In this video, we're going to be proving one of the most special derivatives in calculus, which is the derivative of e to the x's function, because e to the x's derivative is the only function that has the derivative being equal to itself in all of calculus in all of the real world. We're going to be doing this through the definition for the derivative, given a function of f of x being equal to the limit as our change in x represented by h goes to 0 of f of x plus h minus f of x divided by h. From this, we can apply it for our function of e to the x to find its derivative by the definition of the derivative. So the limit as our change in x represented by h goes to 0 of e to the x plus h minus e to the x divided by h will be the definition for the derivative of e to the x. This will be equal to the limit as h goes to 0 of e to the x times e to the h minus e to the x divided by h. And the reason why I can do this is because of an exponential property, which states that a raised to the b plus c power is equal to a raised to the b power times a raised to the c power. So if I expanded e raised to the x plus h power into e to the x times e to the h as so. From this, we can factor out e to the x in the numerator to get the limit as h goes to 0 of e to the x times parentheses e to the h minus 1 divided by h will be equal to our derivative of e to the x. From this limit, we can take out e to the x because e to the x relative to this limit is actually a constant. And the reason why it's a constant is because this limit has to do with regards to our change in x, the variable of h. So when h approaches 0, x is not approaching to 0. X is not affected when h is going to 0. Therefore, we can take out e to the x outside of this limit to be equal to the limit of, as h goes to 0, of e to the h minus 1 divided by h times e to the x as a result for e to the x being a constant of our limit. And we can do this because of a limit property, which states that the limit as x approaches to any variable of n or number of n of a constant represented by c times a function represented by f of x is equal to c times that limit as x goes to n of our function of x. So we have obtained this limit as a result. And from this limit, we're going to be performing a series of algebraic manipulation in order to derive our specified derivative of e to the x. And what I'm going to do is, I'm going to assume e to the h minus 1 being equal to the variable of n. From this definition of the variable of n, we can find e to the h being equal to n plus 1 by adding 1 on both sides of the equation. And from this equation, e to the h is equal to n plus 1, we can find h to be equal to the natural log of n plus 1. With these two definitions in place, we can analyze what would happen to the variable of n as x, or as h rather, approaches to 0. When h goes to 0, we can analyze what happens to n by analyzing e to the h minus 1 is equal to n. When h goes to 0, e to the h will approach 1, and 1 minus 1 will be equal to 0. Therefore, n will approach 0 when h goes to 0. And with these three definitions in place, we can rewrite the limit in terms of h into in terms of n. So this becomes e to the x times the limit as n goes to 0 instead of h of n over the natural log of n plus 1. All I did was substitute our definitions into this limit right here, which was previously written in terms of h. So now that I've rewritten this, what we can do is we can actually begin to further manipulate this limit. This will be equal to e to the x times the limit as n goes to 0 of n over the natural log of n plus 1 times 1 over n over 1 over n. And when we multiply 1 over n into the numerator and denominator, we will get e to the x times the limit as n goes to 0 of 1 over n times the natural log of n plus 1. And with this, what we can do is apply another limit property, which is the limit of the division of two functions. So the limit as x approaches to a number of n of the division of f of x and g of x representing two functions will be equal to the limit as x goes to n of our first function of f of x divided by our second function as x goes to n of g of x. So we can apply it into this limit right here and rewrite this to be equal to e to the x times the limit as n goes to 0 of 1 divided by the limit as n goes to 0 of 1 over n times the natural log of n plus 1. And with this, we can first simplify the numerator, because we know from another limit property that the limit as x approaches any number of n of a constant represented by c is equal to that constant. Therefore, our numerator, as our variable of n approaches to 0 of 1, will be nothing more but 1. But what about our denominator? What can we apply a limit property for to evaluate our denominator? Well, a limit property to do so will be the limit when x goes to n of a composite function. So with the limit when x goes to n of a function of another function, g of x, will be equal to if we penetrate the limit of x goes to n into our function of f. So this becomes f of the limit as x approaches to n of our g of x. This is another limit property which is especially useful, and I cannot emphasize that enough in future proofs of derivatives. So with this definition of this limit property, we can further evaluate this limit to be equal to e to the x times 1 over n times the limit of natural log of n plus 1. But before we do that, what we can actually do is apply a logarithmic property, which is that since I'm running out of room, I'm going to write it here, that the log of base a, b, raised to the n power will be equal to if we put the exponent in front of the logarithm, n times log a to the b. And this applies to any logarithm with any base. In this case, our base is e. So the value inside our limit becomes e to the x times 1 over the limit as n goes to 0 of the natural log of n plus 1 raised to the 1 over n power. And with this, what we can do is we can now apply this limit property to evaluate the denominator, which will be equal to e to the x times 1 over the natural log of the limit as n goes to 0 of, if I scroll up, of n plus 1 raised to the 1 over n power. So the limit when n goes to 0 of n plus 1 raised to the 1 over n power of this natural log. And what is another limit property that we can apply to help us further derive the denominator? Well, we know the definition of e in terms of a limit is e is equal to the limit as x approaches to 0 of x plus 1 raised to the 1 over x power, which is also equal to the limit when x approaches infinity of 1 plus 1 over x raised to the x power. These are two special limits which define the variable of e in terms of a limit. So we can apply this into the quantity inside our natural log. So the quantity inside our natural log becomes e to the x times 1 over the natural log of e. And what is the natural log of e? The natural log of e is nothing more but 1. So this becomes e to the x times 1 over 1, which becomes e to the x, proving one of the most interesting and unique derivatives in calculus, which is the derivative of e to the x is equal to e to the x.